Hello, in this video we are going to solve some numericals on T-beams. There are only three types of problems, and if you master it, you're through. And those three types of problems are based on the formulas which have come in this slide. Case 1, neutral axis lies in flange. Case 2a, neutral axis lies in web, not in flange, that is below the flange. But df, the depth of the flange, is less than 3/7 xu. Now 3/7 xu represents the vertical part of the stress diagram, and case 2b is neutral lies in the wave, that is below the flange, but df is greater than 3/7 of xu. So these three cases I'm going to show you three problems. Problem 1. T-beam of effective flange with 1200, thickness 100, width of 300, effective 560, reinforced with 425 bars. Calculate MR, that is moment resistance, M20 and 415 used. So what do you do? As if it is a rectangular beam, find XU. Plug in these numbers. 0.87, Fy is 415, AST is 425, that is the area, divided by 0.36, 20 and 1200. And then use this XU in the MU formula. And see, you use this formula and you found XU to be 82.07 mm. Okay, that is less than 100. So your use of that formula or case, because see, before starting the problem, you don't know which case it will lie to. So best is you assume that is a rectangle. If XU comes less than the flange depth as it has come here, great, your problem is solved. If not, then you try other two cases afresh, not with the same XU. Alright, so now you look at second one. T-beam of effective flange with 1200, thickness 100, width of rib 300, effective 560, there is 628 bars. And we have same thing, M20 and 415. So now we will assume that it lies, the df is less than 3/7 of xu. So we'll use this formula for compression, where the first part of the expression is assuming that full width of the web goes up to the top, and second is the balance of the flanges into df into the stress. These expressions we had derived also earlier. So now you have XU as 0.446. So you plug in the numbers out here and you get XU. And see, surely it is more than 100. So and if you find 3/7 of this, 3/7 of XU, that will be more than df. So then this case is justified. For mu, very simple. Take the first part of this expression, total compression, multiply with the corresponding lever arm, d minus 0.42 xu. Second part, you multiply corresponding lever arm, d minus df by 2. So you plug in the numbers and you get your moment capacity. Now the last case. A T-beam of effective with 1200, thickness slab 100, width of a rib 300, effective is 560, 525 bars. Area is given to 455 mm square of 525 bars. Find ultimate moment resistance. Actually, there is an error in calling. We should call limiting moment resistance. Okay. Material is M20 and steel is 415. Now neutral axis lies in the web, but df is greater than 3/7 of x. And in this case, if you remember, we use yf. So total tension is this, and total compression, similar expression, but instead of df we are using yf. You find out, and yf is given, this yf is equal to 0.15 xu plus 0.65 df. You have to remember, it's the expression given in IS code, and we are accepting it. So using these two, you see, that is tension equal to compression, and yf is equal to 0.15 xu plus 0.65 df. you will be able to find XU as well as you will be able to find YF. YF you can treat it as equivalent DF, that is depth of the flange. And once you have this in place, all you do is write expression for moment. First portion again is thinking that this web is the width of the beam and goes up to the top of the beam, and second part is remaining of the flange multiplied by the lever arm. So when you plug in these numbers, you will get the total. Now you see the key thing here is how do I know beforehand which case it lies. So always assume it as a simplest rectangle. See what XU comes. If XU comes more than flange depth, which in our case, in all cases it was 100, then obviously your first assumption was wrong. So you try second or third. Whatever answer you get, you check up with 3/7 XU. And that way, second, the 2A and 2B are little trial and error. But then marks will be accordingly. So, thank you.